Hi, this is Chris. And because a lot of people couldn't attend the AI engineering meetup where I gave this talk about fine-tuning vision language models, I wanted to provide a recording for those who were interested and reached out to me. So to be a little bit more precise, it's not just fine-tuning in general, but fine-tuning for classification tasks. And the vision language model that I used for this was Qwen3-VL. And I wanted to give this presentation to be very hands-on. So what I'm basically doing is to describe my journey about how I built EduGraph, an open source solution for education, and how I proceeded in the fine-tuning endeavor there, and which technologies I used, and my insights and my learnings. So what is EduGraph? EduGraph is like a very simple application where you can provide any form of learning material. You can try it out yourself, like with this URL. It's a demo though, so be gentle. But you have a couple of examples to choose from by default. And what it simply does is it takes a learning material and tags it. So on the right, you can see 3 different dimensions: area, the orange, then blue, ability, and green, scope. And when you look at the left, you have a very simple math worksheet, which is about teaching addition. And it has something called a 10 frame on the left and then integers on the right, which is a little bit of a segue and to give kids a transition from counting into adding numbers. And on the right, we can see that the integer addition is the area that was identified. Then the ability, that is cognitive ability. Here is a procedure application. And then in the scope, we can see a refinement of the entire classification, which is, for example, saying that it's about Arabic numerals and not, for example, Roman numerals, that is about base 10 addition and not, for example, binary addition, that it contains numbers without 0 and without negatives, because that is a different concept, different difficulty level. And as mentioned, that it contains a 10 frame as a support for the student. And also that we're talking about numbers smaller than 10, also in the results, so that there's no 10 carry involved. That's a very fine granular description of a competence that is being trained here. On top of that, I also added a similarity search so that you can find other learning material that trains the same competence. And not only does it allow for similarity, but also these tags are just more than simple tags. They're actually connected with each other. So for example, there is areas of math that build on top of other areas of math, for example, decimal addition and fraction addition, integer multiplication, integer subtraction, that are built on top of integer addition, but also with numbers without 0, that there's, of course, numbers with 0, etc. So basically, this is not just some hierarchy, some taxonomy, but there's also other relationships between these entities that describe how we learn. So to achieve this and to basically have something that, a structure that describes these entities and these labels, I needed to create an ontology. So before doing anything related to AI, I needed to come up with a structure to describe these competences. And what is an ontology? Well, the most famous ontology that basically everybody knows is the periodic table of elements. It doesn't just give some names to the elements that we have, but it also groups it and puts them into relationship with each other. And actually, there is a graph representation of this periodic table of elements with these group relationships and also other chemical properties. And that is the ontology of chemical elements, OCE. So if you ever want to check out how that then looks like in a more formalized way, more machine readable with actual graph queries that you can run on them, and you can check out this ontology. Unfortunately, in education, especially in the open source area, in the proprietary one, there are ontologies. Numerous is probably, who knows how many there really are and how good they are. But at least we can say on the open source world that there is really nothing. This is the closest to a proper ontology. And well, as you can see, it's not maintained. The actual ontology file is defect. There is no license information and no proper release. So I really had to start there from scratch. And the good thing is that I already have a background in this from my consulting experience in the US, where we were not working directly on an ontology, but where we were discussing different concepts of ontologies, both like from academia, but also from other examples. And so I already had a good idea how to build such an ontology. And I, over a few months, had refined the approach that I wanted to go for. Then at the point, like, was happy enough to like say, like, okay, I have something that is good enough for primary school math. And I also wanted to do this in a proper way. So like say like, hey, how do you actually like maintain an open source ontology properly? How do you deal with the different file formats? How do you build releases? How do you link types for different programming languages to this ontology? And how can you automate that? And so all of that is contained in this repository here. If you are interested in how to build such an ontology, you can look into Protege, where there's a lot of example ontologies as well. This is like a little screenshot about like how in Protege the ontology looks like that I built. We have some on the top left, we have some object properties. On the top right, we have like kind of like how these relations break down in trees. And then in the bottom, you can see like that, as you would assume for an ontology, that there's also like fields that's here for the fraction division, for example, which you can use for definitions or examples, etc. But I will not go too much into detail about how to build an ontology, because that's really like a world in its own, where you can probably do an entire lecture series about. Honestly, like if you have done anything ever with entity relationship diagrams or similar, then you will probably have an easy time to get into this world. So now we have our ontology, and the first question now is like for our classification task, which base model do we use? So there were various candidates that I could have used for base model. There is for sure like certain better or worse options here for different use cases. Like a little bit of preliminary research like showed me that Qwen3 is probably a really good choice for my use case. The important thing for a base model is that it's under a permissive license, I would say, which Qwen3 is under Apache license, so that you can relicense your own models as you want, either proprietarily or in my case, under a different open source license. So, but other than that, it would be really interesting to see how the same would look like with other ones. And because everything I do here is open source, actually, if you're interested in trying it out with Llama 4 or Gamma 3, you can fork the repo. And 80% of the code will probably be the same, 20% will be probably adjusted, and you could figure out how it compares. And let me know. That would be really fun. Now we have our base model, as I said, in our case, Qwen3. You can now either do directly training, or you can do an intermediate step, which is what I did as well, which is called knowledge infusion. So knowledge infusion is explaining the ontology to the model. And there's also one of the cool things about having an ontology already, that you can actually already like train the model on something that doesn't require hundreds or thousands of examples, but really just like based on how you defined labels and the relationships you put into it. And the way you do it is that you kind of like play a game of Jeopardy between the ontology and the model. And the way that works is that, or like the way Jeopardy works is that instead of asking a question, you're giving the answer, you have to answer with the question. And so the resulting data set for this looks a little bit like this. So like here we have on the left, for example, definitions. Deductive reasoning, for example, is like a form of logical inference that starts with an observation or set for observations and then seeks to find the simplest and most likely explanation. And then the answer for that is abductive reasoning. As you can see, we are doing two things here already. We are already like training a little bit on the response format that we are looking for, and at the same time on the terms of the ontology. And this will already like improve the accuracy of the model by quite a lot. But in my case, it also showed that it would peak out on a bit higher. So it's in the token accuracy. So without this step, it's still almost as accurate, but it's a little bit more accurate this way. So after we've done our knowledge infusion, we go into supervised fine-tuning. What is supervised fine-tuning? For those who don't know, it is very simple. You give something an example worksheet in this case. So I trained everything on worksheets, and we're going to see later why this is actually a good idea. And I'm very happy with that choice. And then the model basically does a classification, and then it compares with the output that would be the correct one. So there's basically a difference between the correct and the classification and the output of the model. and that will readjust the weights based on correct and incorrect answers. So for doing this, I needed first, because just like with the ontologies, open source in education is a bit of a sad story. I also had to create an own worksheet generators. But actually, that was a good thing, because generating the worksheets together with the labeling in one go gave me like a high confidence that I have a really good training data set. And it also made it very easy for me to adjust the training data set. So basically on the left, you see like different types of worksheets. And on the right, you see like how each of these modules for each worksheet looks like. So it's very easy to do this with existing agent models, coding assistants. Once you have like a very simple module structure and you tell it, hey, do it like in this module structure, but now for this other worksheet idea that I have here, then like it's really fast at generating those. There's also some libraries for like reusing different kind of problem generators, especially for arithmetic. So generators that give you like different kind of problems on the worksheets. And then I can use the parameterization that I use inside of the worksheet also as the parameterization for the labeling. And then I get a very consistent labeling. And even if there is a mistake in there, then like I can, it's still very easy to fix and to regenerate the data set. So the output of this, then the data set comes out of this like this. So you see on the left, the little small boxes, those are the worksheets. And then on the right, you see the example classification. And the training itself is really not that exciting. Like it's like most of the code is about either infrastructure, or it is about the training code generation, or it is about like moving files a little bit back and forth, and then also for the publication of the model on Hugging Face, etc. Because I want this all as like a nice pipeline, as everything really smooth and under my own control, and including cost control, which we're going to talk about as well. But the actual, that you see on the left, this is all of the real code for the actual fine-tuning, both for the knowledge infusion and for the multimodal training. And that's it. So like, as you can imagine, like if you want to use this for another model, it's not that hard to accomplish. And that is so nice because of the model architectures are like leaning into fine-tuning nowadays much better, in combination with things like Hugging Face transformers, which help a lot to simplify the training process. Then, now that we're done with training our model, the fifth step is distribution. And because I host those models like as open weight and open source both, we are publishing them on Hugging Face and make it really easy for users to use it. Like I have an extra step in there, which is called quantization with Llama CPP. And that makes it easy to host this yourself. The quantization is kind of a form of compression for the model. And it helps to run it with on a relatively humble infrastructure with consumer-grade graphic cards, which is also very cost-efficient. So on the left, you can see like the installation instruction for typical Llama CPP. And then you just download two files. The one is the actual classification model that I trained, and the other one is the Qwen projector. We can do that because we are not actually training weights on the vision model itself, but only on the layers above. And then you can reuse the original vision projector from Qwen3. And on the bottom right, you can see how you spawn a fully functional inference server with a web API. What were some important insights that I collected during this journey? So first of all, at least for classification, fine-tuning is a game changer, but I can also already see how it's really good for many other tasks. So originally, I did a zero-shot large context experiment with Gemini 2.5 Pro, which uses about between 100 and 300 billion parameters. And like with that, I achieved like a 35% token accuracy and had a really inconsistent output format. And this whole thing, like in the worst case, in the best case, I think it took like 10 seconds, but in the worst case, it usually took like about 30 seconds on an entire GPU cluster, because otherwise you're not able to run such big models. And that means that was a substantial inference cost. And with Qwen3-VL, with a 4 billion instruct model, so it's not even a thinking model, it's just an instruct model and only 4 billion parameters, fine-tuned with about 550 examples in total, I get a token accuracy of 99.8%. I get a very reliable output format. I still have to see an example where the output format was not consistent with what I trained it on. And I get a 1 second inference with a consumer GPU. So this would be extremely fast, much faster on a real data center GPU like an A100 or more. And so that means that this also has negligible inference cost. Also because you don't need so much VRAM, and VRAM at the moment is one of the most expensive resources. And this was the first one. So it's absolutely worth it for classification, 100%. And the other really interesting thing is that it was not just good with regards to accuracy, etc., but also I trained it only on worksheets. Like as you can see on the left, and you can see on the left these worksheets that don't have any text on them. So there's no instructions or something like that. They're purely like the actual math problems. So I really trained them on the math problems and not on any kind of like other parts of the worksheet. Usually you will have a worksheet on it like this trains addition or something like that, right? So there's going to be instructions. And the fascinating part of it is that training it this way, the vision language model really grasped the concept I tried to train it. And like it worked just as well with a photo, like the one on the bottom right, which is not far away from anything in the training data set, and something like a Wikipedia article on the top right. So the interesting thing is that like unlike old OCR models or similar models, you are training it in a very different way, like in a much more flexible way, and makes it much more viable to do fine-tuning as long as you're choosing what you use as examples. If you do that, and if you put a little bit of thought into it, you can get amazing results beyond the actual training data that you are giving it, and like it can learn in a much broader way than at least I expected, and I would say that most people would have expected in that case. The second thing is that if you train small models, that is inexpensive. So on the top you see like the hardware that I trained the model on costs about $8.84 per hour, and a training run here, knowledge infusion plus the examples, takes about 40 minutes. However, I only have to do the knowledge infusion if I really do substantial changes to the ontology. So that's not, I don't have to run that even. So like you can see that a normal training run where I only train on new examples would maybe be like something like $2 or $3. That's how cheap it can be. What I don't like about any of the abstracted away training, that it's like oftentimes very difficult to understand how much you're going to pay up front. Oftentimes they don't give you good predictions, and you can easily run into a scenario where you pay 10 times or 100 times more even than you would expect from a training, because you don't see the actual hardware and you don't really have full control over it. The way I did it, I completely trained it on virtual machines, so I have full control over the entire cost. There's no surprises, nothing. Another cost factor is inference. And what I found really amazing is that when you have the ability, like this is mostly with the hyperscalers like AWS and GCP in Asia, and you have the ability to provide an inference server that can scale to 0. And that can wake up in a relatively fast time. So in my setup, what I did on GCP is that I have an API server with 1 CPU and 1 gig of RAM, and it's always on and costs me about $12 per month. Most of all, it's just like a very simple API server. It wakes up the inference server if it is not there. So it will basically like retry until the inference server is there. And the first request will start the wake up, and then it keeps polling until the inference server returns a result. And this allows to have an inference server that will be usually online something between 10 to 15 minutes after it was woken up, available for like $5 to $10 a month for something like a demo. But even if you just generally have like bulk usage, like it's the same thing. It's that you can like do just a lot of inference at a time and just pay for the time that the inference server was really online. Because otherwise, this like smallest inference server that you can think of, like a 4 CPU with 16 gig of RAM and an L4 GPU, that will cost you $350 per month. And with scale to 0, it's only $5 to $10 per month. And that is amazing because it enables to train these, not just only to train these models and to fine tune them to use case, but to also like have a relatively relaxed relationship with your inference server costs. Because I've seen this too, that like when you, for example, train like a Gemini and you want to host like your fine-tuned Gemini, then you don't have this option of scale to 0. You will have to deploy it like all the time, like full time. With a Gemini Pro, like that would be like something like $1,500 a month. But if you fine tune an open source model, well, then you can use the scale to 0 options, host it like that, and have a cheap time. Also, of course, you can run them locally if you want to, right? Because they're small enough to work on a consumer graphic card. So this was some of the things I wanted to share on my journey. I wanted to say thank you for taking the time to listen. And if you want to connect on LinkedIn, happy to do that. I also wanted to mention that that everything here is open source, so you can have a look at it, and you can fork and play around with it, and give me feedback, or like also just contribute. It's for a good cause, so why not? And the other thing I wanted to say is that I didn't talk about the similarity search yet and how I built the embedding model, which is, I think, also a very interesting topic, but probably too much for only one session. So you're more than welcome to let me know if you're interested in that. And I'd be happy to provide another talk. Thank you so much. Bye-bye.